number of years ago in Germany, a man gave to the world a new concept. It shook the scientific world from top to bottom, changed the course of human history, and gave us the atomic age. The man, Albert Einstein. The concept, relativity. That strange, fantastic relationship between time, distance, and mass. Now, an important part of that concept can be expressed in a simple equation. E equals mc squared. Energy equals mass times the speed of light squared. The equivalence of mass and energy. The basic formula that unlocked the secrets of the atom. But equally, if not more important, is that relationship between time and space. Now, we can't speak of the equivalence of time and space. They're not exactly equal. But we can say that they are relative, or they are all bound up together. Just obtuse theory, you say? Well, maybe so. But every day there is new concrete evidence to prove it true. When Dr. E.O. Lawrence and his associates at the University of California designed the 184-inch cyclotron, they didn't laugh at this theory. They accepted it as true, and it's a good thing they did. In the cyclotron, tiny particles are accelerated in magnetic and electrical fields until they approach the speed of light. This rotary condenser at the side of the cyclotron compensates for the increased mass of the particles, which occurred exactly as Einstein had predicted it would. Let's suppose that at some day in the Buck Rogers future, you decide to take a trip to a planet satellite of the star Sirius. As long as we're supposing, let's say that your atom-powered rocket ship is capable of traveling at 99,999,999 100 millionths% of the speed of light. Now, of course, this is very close to 186,284 miles a second. In view of the fact that Sirius is 9 light years from the Earth, it would take just a little over 18 years to make the round trip. Naturally, you'd plan to take a large supply of food, but all you'd need would be a sack lunch. Traveling at this speed, not only would your watch slow down by a factor of 70,000, but your heart, respiration, digestion, appetite, all would slow down in the same ratio. You could leave the Earth some morning right after breakfast. By the time you got to Sirius, you'd be ready for a sandwich. And when you got back to the Earth, you'd be just hungry enough for a good dinner. But then would come the surprise. You'd find that while you were only 1 day older physically, your children would all be grown up and through college, and all your friends would be 18 years older than when you left them just 12 hours ago by your watch. A concept such as this is almost impossible for the human mind to grasp. It's so far beyond our normal experience. But maybe this will help. First of all, listen to my heart. Now, let me start the clock so that you can become accustomed to the rhythm of its beat. The yardstick. It looks normal, doesn't it? But if we could accelerate this room and everything in it to the speed of light, 186,284 miles a second, time would stand still. My heart would stop beating, yet I wouldn't die. The clock would cease to run. And everything would squeeze into a line, infinitely thin. Now, we can't speed the room up to the speed of light, of course. But with the magic of some very special photography, we can show you exactly what would happen if we could speed up the room to 90% of the speed of light, 167,000 miles per second. Are you ready? All right. There's our speedometer. And we're going to travel in that direction. You notice what's happening?
My voice has changed. 12. Listen to my heart. Let's go back to normal now.
This time, we're going to accelerate vertically instead of horizontally.
Now the yardstick is 18 inches long, approximately, when we hold it vertically. When it comes back to 36 inches
when we bring it to the horizontal. When the room was accelerated, everything seemed normal to me. My voice sounded the same. The rhythm of the clock remained constant. The yardstick seemed the same in both directions. That's because I was accelerated along with the room. But you, as a stationary observer, were aware of the changes. Now, of course, the visual effects which you noticed were achieved in this case by the use of a Panavision lens, a variable aspect ratio lens. But the effect was exactly the same as if the room had actually been accelerated to 90% of the speed of light. These are called relativistic effects. They are based on mathematical formulas that are as common in the workaday world of the nuclear physicist as 2 times 2 equals 4 is in our world.